So the next speaker is Tuomo. He's going to talk about X-ray polarimetry of accreting millisecond pulsars. It's yours. Thank you.
Okay, thank you. My name is Tuomo Salmi, and I will talk to you about X-ray polarimetry of accreting millisecond pulsars. And this is a work that I was doing last year when finishing my PhD in University of Turku, but now continuing in Amsterdam with with many same collaborators, but also a few new ones as well. So introduction to this was actually given already in the first talk, but just to quickly recap, one of the main goals in this study is to find more information about the properties of the unknown properties of the inner core of the neutron star and constrain the equation of state of such high density and cold matter. And millisecond pulsars are one promising class of neutron stars that can be used in order to achieve this goal by observing X-ray pulses that encode information about the mass and radius and of course, therefore, the equation of state. And as explained in the previous talks, it's a polarization that can be used together with the pulse profile modeling to get even tighter constraints for equation of state by providing more information for the neutron star geometry, which is coupled with the other parameters of the neutron star model. And the class of neutron stars where this is especially useful is accreting millisecond pulsars, where we have, of course, a pulsar that is accreting matter from a companion, from accretion disk, and flowing along the magnetic field lines to the magnetic poles of the neutron star, heating the surface, and then assumingly creating two hot spots, which then radiate thermal radiation in X-rays, but this radiation is then still reprocessed with the particles that are flowing towards neutron star surface, and due to this reprocessing and this Compton scattering that happens on top of the neutron star surface, we see that the photons will be shifted towards higher energies, and also they have different beaming pattern, and also because of this reprocessing, the originally unpolarized radiation will be polarized during this process. And okay, all these effects, in addition to this light bending and strong gravity, relativistic effects, geometry, etc., should be taken into account when modeling these sources. And the main technique is, of course, pulse profile modeling, which is something that has been developed during multiple years, almost a few decades already, and recently it has been also nicely used to constrain neutron star mass and radius for rotation-powered millisecond pulsars using nicer observations from Riley and Miller for two different pulsars. But of course, in those cases, we talk about rotation-powered millisecond pulsars, so there is no polarization needed for those, and the emission model of this radiation is very different than in accretion-powered millisecond pulsars. The transportation of the radiation is in principle similar in those than in accreting millisecond pulsars. So basically, it just has to take all the relativistic effects into account, and as Vlad already explained, these same things were accounted for when calculating polarization angle as a function of phase in his paper from last year. And now we have a model that should be able to calculate the polarization as a function of pulsar phase, as well as the non-polarized flux. So in this figure, this is the same figure that was shown in the first talk. So it is showing how you can break the parameter degeneracy between spot co-latitude and the observer inclination when having additional information from the polarimetry. So if you look only at the uppermost row, you see that the normal flux is almost similar for these two different cases where you have either theta equal to 50 and I 20 or theta 20 and I 50. But of course, well, also the polarization degree is very much the same. But if you look at the polarization angle as a function of phase, this is completely different for these two cases, and therefore polarization could be used to separate these two cases and therefore help to measure mass and radius as well. But that is something that is relatively well known, how the radiation transports from the hotspot frame to the observer frame. But what is more uncertain, I think, is the emission model. What is causing the emission in the first place in the neutron star surface, and more accurately said, what is the function of the intensity? What is the intensity as a function of energy and emission angle? Here, mu is the cosine of the emission angle, and E is energy. And also, what is the function of polarization degree as a function of energy and emission angle? And so far, what people have used, or at least what we used in our previous paper, was this relatively simple Thomson scattering model, which is based on the earlier works by Sunjärvi-Titarsuk and Vironen Poutanen in 2004, where you have this sort of dependency of polarization degree as a function of emission angle for different photon energies. So you see that when mu is equal to 1, so the emission angle is close to 0, so emitted almost in the vertical direction, then radiation is very little polarized. But if the radiation is emitted toward high angles, then it might be like almost 25% it's polarized instead. But this is something that is still quite simple model, and recently there has been development to make a more sophisticated and more physical model based on complex scattering in a hot electron slab on top of the thermal layer, where the radiative transfer equation is solved using exact competent redistribution matrix. And you see that if you would use this kind of model, you would get very different predictions for the polarization degree as a function of mu, if assuming the same model parameters for the hot slab. Of course, these curves, okay, generally speaking, this competence slab model predicts smaller polarization degree, which is of course not that good as this Thomson would predict, but this is of course more physical, and therefore we should take that into account in our estimates. Anyway, these curves are also dependent on the choices we made on the model parameters, like the optical length, electron temperature of the slab, and the energy of the and the temperature of the seed photons. So by changing all these parameters, you could also get very different results, and therefore we needed to have a big grid of these models, which could be then interpolated and taken into account uncertainty in all these parameters. And okay, this is just some formulas, and I won't spend time on here to explain the competence slab model. I will just remind or focus here on the output. So the model gives us the Stokes vector I, so basically intensity and Q, Stokes Q parameter in the frame of the hotspot, since U parameter is 0 by definition, and the V, which describes the polarization, circular polarization, is assumed to be 0 because we don't expect to have sources for circular polarization. But anyway, when we move to the frame of the observer, then we will get the third Stokes parameter, which is U. So in the end, we have a intensity Q and U as a function of time and energy. So we have a normal pulse profile fitting with which we work with using only I, but in case of working with polarimetry, we can fit simultaneously I, Q, and U. And this is something, okay, we have not observed yet because the instruments are still coming. And next is XP, and EXTP will follow later. But XP is the first one. But these both instruments use these gas pixel detectors basically, and where this every photon that is hitting the instrument, they will cause by photoelectric effect, they will emit electron, and the direction of this electron will tell us about the polarization state of the radiation. So basically, we don't observe directly Stokes parameters, but we obtain first track of these photoelectrons, then convert these to angles corresponding to each photon, and Stokes parameter corresponding to each individual photon. And then by summing over each individual events, we get the total Stokes parameters for the for a certain data set. This is something that has been developed in a software tool like XPOpsim, which we used in a paper early this year to simulate Stokes Q and U data for XP, and then estimated using this data how good constraints for the Newton-Charge geometry we could obtain using this. Even this work is still going to be improved using a revisited instrument and model information, but I will still briefly to give you some rough ideas. I will just give you information about that work that already was published. So in this work, we try to estimate how accurately we can measure observer inclination and spot collectitude as a function of the exposure time of XP using a similar source like Zach's J1808. And as assuming different setups for the model. So we can see here in this figure on the right that the uncertainty, average uncertainty in I and theta, the 95% is credible interval, improves as a function of exposure time, but it depends a lot of which parameters you assume to be the true parameters of your model. So of course, if the setup is different, your polarization degree might be higher or lower, and then therefore you might end up with much tighter or much less tight constraints. For EXTP, of course, these estimates should be scaled so that even smaller exposure time, a couple of times smaller exposure time would be enough to obtain the same accuracy. But taking into account this large deviation between different model setups, we can roughly say that 10-degree accuracy in these geometrical angles is something that could be achievable even with XP. At least assuming this was still assuming the Thomson scattering model. With the Compton scattering model, it might be a little bit more difficult. But anyway, if obtaining about the same accuracy, we can try to think how much that helps in measuring mass and radius. There is not very detailed studies about how exactly that will affect the mass and radius constraints, except there is one test which was done in this 2018 paper, where we simulated data and then fitted it without prior information in I and theta, and with prior information where that was assumed to be produced by polarization measurements. And we saw that the mass and radius both improved if assuming the 6-degree accuracy in the measured I and theta. But this is there is more improvement in mass than in radius. This improvement is maybe a little bit hard to see from this, but it is maybe not a very good example, because in this case we had also another observations which already had excluded the opportunity to have switched inclination and theta. So in other cases it might be even more relevant and even better to have polarimetric information. But even in this case, where there was already information from optical and radio, you can still improve your mass and radius, and especially if you fit simultaneously all the Stokes parameters, which was not done here, but it should be done. Then it's expected to have a greater effect, of course. Okay, but then that effects on mass and radius is not everything you can obtain using polarimetry. So the last thing I would like to mention is the effects on the magnetic field configuration. So as we know from the rotation powered Millisecond pulsars, it looks like the antipodal symmetry is not very common. And what about accreting Millisecond pulsars? Can we measure that from those? And this can be measured using polarimetry. So if we would have 2 spots, and if the other one is not hiding behind the accretion disk, which might be sometimes the case, but if the both spots are visible, then we can separate the 2 cases using polarimetry. So whether or not these 2 spots are antipodal or non-antipodal, in this work we produced data using both setups and saw that there is a very different curves in the polarization degree Stokes Q and Stokes U as a function of pulsar phase, and the curve and the data looks very different if assuming a different geometric, if assuming different magnetic field configuration. And we can even fit the data and get constraints for all the parameters, which were in this case the location of both of the spots, so also the secondary spot co-latitude and the phase difference. So this was just fitting pure polarimetric data without the normal pulse profile modeling. So of course, when combining with the normal pulse profile modeling, all the parameter constraints should be much even enhanced. But this is providing additional information that should be combined with the modeling of the total intensity. Okay, but this is what we have learned. So Newton's geometry definitely can be used to, can be definitely constrained even using with XP, and it's also possible to constrain the magnetic field geometry, and it should be used together with the normal pulse profile modeling, for example, using XMM analyzer. But with EXTP, the cool thing is that that can observe everything. So we can use EXTP to have a good resolution in energy, in time, in polarization, and simultaneously fit all the Stokes parameters. And assumably, very good results also should be possible for mass and radius. And the future, our current work is on developing this more accurate emission model, and then analysis the real data as soon as it is available. Thank you.
Thank you. So any question or comments? Okay, so Amrita, so you can go ahead and speak, ask your question.
Hey, hi. Thanks for a great talk. I have a quick question, which is, during the evolution of the outburst itself in AMX space, as you're ramping up from this initial rise and then to the flat top, kind of like a canonical shape of an outburst, what is your expectation for polarimetric evolution?
So that's a good question, which I think has not been studied or talked enough yet. So the general idea is that this doesn't change a lot. I think if it would change, it means either the optical depth or the electron temperature or the seed photon temperature would change as a function of the as a phase of the outburst. So in principle, I think if any of these parameters changes, then the polarization would also change, and that would be maybe good to think more how important that would be. But I think that's a relevant question, and I'm not sure how much that could affect.
Thank you.
Okay, so so I see another hand. So perhaps you can ask your question through question and answer window. So I think it's time to take